Here's a diagram of the clotting process. If we have a damaged blood vessel, it's leaking. One, the blood vessel will contract so that there's less flow through. Platelets start to stick to those rough edges and plug it up and secrete chemicals that help further block things. And then the body can grow, recover, and heal itself, assuming all the processes are working properly. So blood, about 55% of it is the liquid, 45% are those cells and the platelets that we already talked about. The liquid part is mostly water, no surprise, but yes, it is thicker than water. It does have a variety of proteins functioning in things like digestion, helping carry nutrients around. Additional protection, I would say part of the clotting, some immune roles for the proteins, things like that. And then we have miscellaneous other dissolved stuff, the gases, the nutrients, the waste, salts, things like that. Again, different white blood cells, lots of different ways that they can help identify and attack any sort of dangerous invader. Blood vessels, three major categories, and then we can recognize within that. So arteries are the ones going out from the heart, and they branch into smaller ones and eventually into the tiny capillaries. Capillaries, basically one blood cell can fit through at a time. So there's a lot of surface with the tissue around, and this is where we have the stuff in the blood released out to the tissue, the waste of the tissue going into blood to be carried on from there. The veins are carrying the blood on back from the tissue towards the heart again. So except in the case of the pulmonary vein that's coming from the lungs back to the heart, the rest of the veins are carrying the blood where we've used up the oxygen. Hemoglobin is reddish when it's got oxygen, bluish when it's not. Now, getting the blood to your body is the most important part. Getting it back, well, that's important, but not quite as essential. So the arteries tend to be deeper down, more protected inside the body. The veins near the surface. So if your skin is pale enough, and you can see blood vessels in your skin, they look bluish. And so you get that look to the veins at the surface. But you've probably noticed, if you cut yourself, it does not look blue, it's red. Why is that if it's the vein that is bleeding? Well, the color of the blood, red if it's got oxygen, blue if it doesn't. When you've got a cut, that blood's exposed to the air. Lots of oxygen there. So your blood gets oxygenated, it's nice and red, except it's not where it's supposed to be. It's not inside you, so that's not doing you any good. So again, the heart pumps blood into the arteries. This will flow into smaller and smaller branches, into the capillaries. Capillaries interact with the tissue. Oxygen is taken up by the tissue. Nutrients taken up by the tissue. Waste from the tissue goes into the blood. And then the capillaries drain back into smaller veins, venules, into the main veins. Also, some of the fluid can leak out from the capillary. Capillaries are much thinner tube, so you do get some leaking there. You shouldn't be leaking from your main veins and arteries, that would be bad, but capillary, you do get some leaking, and so fluid gets out into the body, and this drains into the lymph system, which goes back into the bloodstream once more. Lymph system also has sets of nodes, concentration of immune cells. So they're picking up on all this stuff, draining from the body and detecting, okay, this all looks good. Or, hey, wait a moment, what's this thing I'm getting drained from the body? It looks like some germ. Uh-oh, kill it. Larger vessels typically have muscle in them, so they're able to expand and contract regulates something of the flow in them, in addition to the force of pumping from the heart. Although all vertebrates have a relatively complex circulatory system, there are important differences in detail, and this relates to the difference in life habits. Two big things. One, do you breathe in water with gills, or do you breathe air with lungs? And also, what's your metabolism? Are you warm-blooded, needing lots of oxygen all the time? Or are you cold-blooded, ectothermic, and not needing nearly as much oxygen most of the time? Air is a whole lot less heavy than water and less dense, so the air pressure is much less than water pressure. Pressure in the blood vessels in the lungs, therefore, needs to be low enough that it doesn't push and cause leaking into the lung. So it needs to not be drastically higher than the air pressure around it. On the other hand, the heart needs to put enough pressure in the blood to pump it all the way through the body. So depending on how big an animal it is, that may require relatively high pressure. So if you've got lungs, you've got low pressure in the lungs, higher pressure in the rest of the body. That's going to be more complicated than having gills underwater, where the surrounding stuff is at higher pressure, and it's harder for fluid in the blood vessels to push out from the gills, so you can have high blood pressure throughout the body. Of course, higher activity levels need a better blood supply to keep giving the oxygen, the nutrients that the body needs. So this relates to the pattern of chambers in the heart. The atria are the parts of the heart that are receiving blood from other parts of the body. And the ventricle, or ventricles, you may have one or more of each of these, that is what's pushing it back out into parts of the body. So for fish, using gills, basically just one atrium, one ventricle, stuff drains in from the body, pushes out to the gills, and from there through the rest of the body. Right past the heart, at the gills, you've got some of the highest pressure before it moves all through the rest of the body. So if the water around were replaced by air, that blood pressure is going to be a problem. And so if we have something, say like amphibian, we're relying on lungs, like this frog here, you have two atria, one that's receiving the blood from the lung area, one that's receiving from the general body. And so you can pump differently to send blood into the lungs. You've got a little bit different in the pressures there. Something else to note, check your pulse. Uh-oh, I don't have a pulse. I'm dead. However, for a frog or a reptile or a fish, they aren't constantly maintaining a high warm metabolism. They don't have to have the heart beating all the time. They don't have to be breathing all the time. They can go for long intervals between heartbeats and breaths. So very different pattern in them than in us. Here we have lizard. And we have some more degree of separation between the two sides of the ventricles, so two atria coming in from the lungs or in from the rest of the body. And the division allows more regulation of how much blood and what pressure is pumped to the lungs versus to other parts in the body. Animal actually has some degree of control of mixing of how much body blood with less oxygen versus blood coming from the lungs is pumped through. In fact, the crocodile group, things like alligators, have a valve that they can open or close to reroute the pattern of blood circulation depending on whether they're diving in underwater or up in air breathing. Birds and mammals have full division into 4 full chambers, 2 atria, 2 ventricles, and so we have separate pumping to the lungs versus to the rest of the body, and separate parts receiving the blood from the body versus from the lungs. Doing all this work, the heart, a very muscular organ, again, special style of muscle, cardiac muscle. We looked at the different styles. It's different from your standard skeletal muscle that's in most of the voluntary, as well as from the smooth muscle in the digestive system. The heart is protected by a pericardial sac that provides fluid around lubrication, so the heart's not rubbing on things. That would not be good. Need the right pressure balance. Too high pressure, and that's making it hard for the heart to beat. The heart is able to signal itself. It doesn't have to have the brain telling it pump. But of course, signals need to go back and forth. The brain needs to detect and say, okay, good, you're pumping at the rate I need, or hey, pump some more, or whoa, slow down. So there is interaction, but the heart is able to maintain its pumping on its own.